Welcome, Daniel.
Hey, hey,
Uh,
good to
Daniel is
good
going
to
to
be
share
here.
with us a presentation about should you, or the question that we want to ask, should you self-host Inference? And he's going to share with us a bunch of learnings and tips and whatnot in this space. So looking forward to it. Oh, yours, Daniel.
Thank you so much. Well, it's great to be here. I'm just curious, are you pulling the slides up or should I? Um, I
Alan,
definitely
are you
can.
there?
I can do it. So I'm
Okay.
already sharing
Oh, yeah,
screen.
there you go. I see your
There you
deck.
go. There you go. Okay, cool. So we get to see the HTML version, not the PDF. So the animations actually move. Oh, all right, cool. Also, I'm in Prague right now, so it's about half an hour past midnight. So I have about 2 brain cells left, but I'm sure we'll get through the material. So, hey, everybody. I guess you have heard a lot about the problems that are involved in serving the largest, greatest open source models out there. I'll take it from a little bit the opposite side. I'll focus on smaller models that are maybe easier to self-host, and we'll talk about whether you should and what the use cases look like that match that. I'm Daniel. I'm CEO of Superlinked. We have an open source inference product out there, which I'll kind of share some learnings from building, just in terms of architecture and what you may want to do when you build your own inference infrastructure. Okay, let's get going. So basically, the basic math of self-hosting versus like paying for GPUs versus paying for tokens basically has to do with kind of a couple different elements. So there is the element of cost. If you can saturate the GPUs, if you can use them properly, if you have enough volume, then you'll always basically save money compared to paying per token. Then there was this famous case study, for example, with Intercom, saving a bunch of money, kind of switching to open source models. You get more control of arguably the most important feature of your system if you self-host the models. So you will not just like lose access, or you will not be susceptible to pricing changes of your token suppliers. And kind of maybe not so obvious benefit is that when you build your product, you build your platform, you get to kind of bundle the inference into the platform, and you can really integrate it with what your specific platform needs, right? What the shape of your traffic is, where that traffic is coming from, or how it's interacting with the rest of your system. The tighter you can integrate inference into your systems, the fewer network hubs you have, and the more kind of tailored it can be in terms of the tuning. And you typically already run on a few different clouds, few different environments, so adding that to the mix is not necessarily that hard. So those are some kind of high-level thoughts around self-hosting. And honestly, you have to kind of start by reflecting. And there are some patterns that, like if you, for example, have, let's say, less than 5 million requests a month, if you don't, already spend, let's say, at least like a couple thousands or 10K a month on the APIs, or if you absolutely need the latest proprietary frontier models, those are the kind of scenarios where self-hosting probably doesn't make sense. But then when you go past those limits, so let's say past 10 million requests per month, if you are okay with the quality provided by open source models, and we'll talk about what that means, how to think about that. Or if you want to bundle inference, as I said, into your own platform, especially if you deploy, we work with some platforms that deploy their software into customers' environments. And if you want to basically bundle inference, bundle the models into that, and have your platform actually work in those environments and all the agents still perform, then that would be another kind of scenario where self-hosting makes sense. Okay, so first question that probably everybody is asking is on the model quality, right? Are the smaller open source models that are easier to self-host, easier to deploy in these different environments, are they good enough? How should we think about that? And by the way, when I say small, I mean, let's say under 40 billion parameters. Basically, those are the models that you can serve on one GPU that's even, let's say, 2 or 3 or maybe 4 generations behind the cutting edge, right? So that's what we mean by small. So this is kind of a first chart that I'll share. And on this chart, we see kind of 3 groups of models, even though the middle group is somewhat subtle in its coloring. So I split it between kind of proprietary models, large open weight models, for which, let's say, you need the latest GPUs and often multiple GPUs to serve one model, and then the small open weights models that fit on one GPU comfortably. And the chart shows the artificial analysis blended intelligence index over time. And I think, if you squint really hard, there are 2 things to notice from this chart. The first is some kind of convergence, right? So the frontier models are kind of not climbing as steep, let's say, as they used to. Then you have the largest open source models, and then you have the small models. And they're sort of still climbing pretty steep. So there is some sort of convergence happening between all the way the largest proprietary models and the smaller open source models. And then you can kind of zoom in and look at, for example, GPT 5.1 and Qwen 3627B. And I think they're like 48 versus 46 in this score, basically. So they're practically indistinguishable in terms of performance. So let's say this was maybe 5 months apart between release of GPT 5.1 and Qwen 3627B. So if you can basically wait for 5 months, you'll get equivalent performance to the frontier in a form factor that's actually very easy to work with. So if your workflow already, let's say, works with this one, then it should be very easy to migrate. So that's one way to think about it. Now, if you use open source models, of course, you are not just left to kind of consume the model as it is off the shelf. You can augment it, right? You can improve it. And just to give you some idea of kind of, is this expensive? Is it complicated? Here is just like very simple demonstration of using a LoRa to fine-tune an embedding model. And I'll mention embeddings a couple of times because we see that it's one of those model types that people self-host first. It's the easiest one to maybe get into self-hosting with kind of search-related models. And so for this experiment, we took the Arctic embed kind of base model, 500 million parameters, and it's a multilingual embedding model. And we ask ourselves, what would it take for it to perform better on legal documents in German? Can a LoRa adapter move a needle on that? And after spending about $1 on the GPU time to train that adapter on basically train split of this first data set, we see that on that specific data set, we got, if we use a combination of legal data and general German data, then we have 18% lift of NDCG at 10, which is like a metric of quality of retrieval. And then even on a totally different but still legal German data set, we have a lift of 8%, which is substantial, right? So this is like beyond frontier. If you look at the generalist frontier embedding model, this pushes past that on legal German documents. And then you have to kind of play with, that there are trade-offs, right? So if we boost the legal German, maybe we lose on totally generalized German tasks. That's why we blend the general German in, and we have, like 0.6 and 2% regression on those tests, but we have those lifts to compensate. So that's kind of the addendum to this story that, okay, this is the basically base models on the open source side, but then you can adjust them to your problem as well. And you can do LoRa adapters, not only for embeddings, of course, but also for re-ranking models, for generative models. If you use generative models to do classification or other types of structured output generation, this also works, right? And the adapter is like super cheap to train. It's very small. It's in this case about 10% of the model size. And modern serving engines can load into memory not just the model, but also multiple adapters, and you can switch between them. So you can have different adaptation for different language or different domain. And again, this works across different model types. So that's just kind of like a quick side note on, when you see these kinds of charts, don't take them as kind of the final state, right? Because open source models allow you this kind of augmentation to approach or even push past the frontier on the problem that you actually care about. Okay. Now, in terms of the total output of the open source AI community, we have, I think, maybe this chart is like a little bit old. Maybe we have already crossed 3 million models uploaded to Hugging Face. I think there is maybe 100,000 models uploaded per month. Of course, not all of those will be state-of-the-art models, but they're, let's say, on the order of hundreds of models uploaded every month that are basically state-of-the-art in their specific niche, right? So there are any amount of niches for models that you can imagine. They're task-specific, so they're OCR models for receipts adapted in different languages, right? And of course, anything related to search, vision, speech to text, just the really broad spectrum of models being available. And most people, don't really take their time to discover what's available. And then it's not always so easy to actually run those models, right? So those are the two barriers that kind of make this not that easy, but the models are there, right? So we have kind of shown that the small models are pretty good in terms of quality. You can even improve the quality quite easily. And there's just so many models available that you for sure have one that solves your problem, right? So that kind of should, take care of the thoughts of like, okay, but small models, will they work for me? So then the next question is, how do we actually use those small models, right? And so we need, you guys heard about different architectures, different setups for inference, for serving. So I'll tell you a little bit about kind of how we see this. This is still back to the economics, right? So we said, let's say 10 million requests a month per GPU in your fleet. That's, let's say, the break-even point. And then past that, you are not paying extra money because you have that one GPU for a month, right? Now, of course, it also depends on which kind of GPU and on which kind of price you can get it. But when we talk about small models, I really mean it that those GPUs don't have to be large. So you can start from kind of NVIDIA L4, A10. Then for models that, let's say, go past 4 or 8 billion parameters, you can grab A100, or now the RTX Pro 6000 is pretty good. And these are, on the order of $1 to $1.5 per hour, of course, based on the provider. These are typically kind of half that. And then you have the H100s and beyond. And that's totally fine, right? So you don't need to go anywhere near anything bigger than those, right? So if you stick to kind of the Sub-40B on the model size. And just to give you some idea on kind of, okay, you have that one GPU and this kind of back to embeddings. If you have like some state-of-the-art reasonable models, you can expect on the order of from, let's say, 50 to 250, 300, or even more 1,000 tokens processed per second, right? So if you have a corpus with a billion tokens, on one GPU, you can make vector embeddings of that in, like an hour or something, because you are doing million in 4 seconds. So that's going to be 4 times 1,000, right? Basically an hour. The latencies, of course, will be much better than any managed provider, and the price will be, something on the order of a tenth of the managed provider cost. Of course, embeddings, again, it's the easiest case, right? It's the easiest to serve. They're typically pretty small. So that's, an ideal entry point to self-hosting. Now, in terms of the topology, we talked about kind of where can your tokens be coming from. So it's either, both the model and the infrastructure is proprietary. So those would be your foundation labs, or the models are open source, but the infrastructure is proprietary. That's all your favorite, third-party inference providers. Or you have an open source based stack that you actually run yourself, and you bundle it into your platform, you bundle it into your cloud, and that's where VLLM or SGLang based serving solutions, some kind of Kubernetes wrappers come into play, and that's where also our open source product exists in that category. And here I have a quick comparison. So I think maybe this is like kind of trivial, but there is a difference between the runtimes and the cluster setups, right? So let's say if you are looking at what's running on the individual box, you would be looking at VLLM, SGLang. There is also TensorRT LLM. And then for embeddings, there is the Tay from Hugging Face, very cool project. So those give you the runtimes to run on individual machines, but then you need to build the cluster around it. And the cluster, kind of open source clusters, of course, are also available. So we already heard about Dynamo from NVIDIA. There is LLMD, and which basically now focuses on VLLM. There is Kserve, and then there is Superlinked Inference Engine. So as you can see here, we don't focus on the large models as most of the other players. We focus on these small models that we have been sort of describing so far. And then we try to make it as easy as possible to serve those models, kind of one-click install into different clouds and that kind of thing. So that's a little bit the landscape. If people are kind of looking at open source inference solutions, I think this is like a good set to start researching from. And in terms of kind of, if you are building one of these clusters yourself, I wanted to share a couple different tips. So one thing that has worked for us is that if you are doing small models, and if the requests are very quick, we are talking 50 or 100 milliseconds in latency. If you take the approach, the traditional routing approach, where the router has a very deep understanding of the worker state, and then top-down decides where each request is going, and then each worker has a local queue, as we see on the left. The problem, if you have many small requests coming in quickly, it's really hard to actually fill up the batches on these GPUs, and therefore you are not using them very efficiently. Because like half a size batch and a full batch takes almost the same amount of time, except half a size batch processes half of the data, right? So instead, we work as much as we can with a centralized queue. We have a NATS Jetstream-based queue. We have a gateway that annotates the requests with some metadata, and then the workers pull from that queue based on them, being available and being able to form a batch, right? So this way, we don't fragment the traffic into the local worker queues, and that alone helped us improve the throughput by more than 50% for these small model workloads. I should say as a side note that the system can also create kind of a direct channel to a worker if the local worker cache becomes important. But we still insert the request also into like a global shared queue. So if that one worker becomes saturated, other workers can start picking the work up. And next, as we start to disaggregate the different stages of inference, we have that kind of shared queue element that can be easily used to chain these different steps. So we really sort of enjoy this design, that there is a kind of stateful queue in the middle. And we chose something that has like very little overhead, so no Kafka, nothing like that. Something much more kind of bare metal and fast. And then you can also have this kind of centralized telemetry attached to that queue, which is quite beneficial and handy. So because then you can do scaling based on that and so on. And then the second trick that's really important with small models is put more of them onto the same GPU. So you have, we talked about LoRa's, you have different models, you have different LoRa's. You don't want to have worker pools that the whole pool is serving one specific model, and then another pool is serving another model. You want to kind of aggregate all those workloads into as shared of a cluster as possible. You want to load multiple models into the VRAM of the same GPU, ideally, because then if you have a traffic that has a bunch of different models, you can serve it much more effectively. So that's kind of the added trick that's important to keep in mind. So then this is how the cluster looks like. You have your gateway, you have your queue, and you have your workers that run different inference backends. We, for example, in our product, have our own inference backends written in PyTorch and Candle in Rust. But we also have, other open source backends available, and we kind of sweep through the parameters, and we choose whatever is best for each model that we support. So that's kind of the topology that has worked well for us, and maybe something you can emulate in your projects. And I wanted to mention kind of something about user experience. So if you are thinking about building an inference platform at your own company, for me, the rule of thumb of kind of how can I make people more productive, more efficient, is when they don't have to talk to each other. And there is, the AI engineers in an organization and the infrastructure engineers. And if they don't really have to talk to each other to achieve their goal, then they can move much faster. So, in our product and in the best products we see out there on the market, the infrastructure engineers, they kind of understand the quotas they have in different zones, different locations. They are there to kind of recover if the cluster hits some kind of big problem. They own the account, and they deal with sort of billing and all of that. And then the AI engineers, they are the ones who come in and they want to create, let's say, pools of compute that their project needs. They want to maybe pin some models, but for other models, they just want to lazy load them into the cluster because they're comparing different models. So they need kind of lazy loading with eviction for certain models, pinning, and kind of capacity reservation for some workloads that they already know they want to be doing. And then, of course, they want to do the inference calls, right? So in our product, everything that happens on the left side is done against the API, and it's super easy for any engineer or data scientist to get done. And then everything on the right is kind of infrastructure as code, Terraform, Helm charts, all of that, right? So two different worlds, and they don't have to interact with each other. And then then our inference cluster kind of sits in the middle. So I think that's a really good design for any kind of internal platform that you might be building. Just treat the AI engineers as your internal customers, basically, and give them a good experience. Okay, and then finally, let's say you are now bought into using small models. You have some idea of how your cluster should look like. Now the question is, okay, what can you build with this, right? So I'll talk quickly about one example agent. We have in our repo a couple different examples. So in this agent, it's actually written in, I believe, OpenAI Agents SDK. But of course, there are other harnesses that you can use. This one is a contract review agent. It extracts facts from contracts. It has some vision capability to see if contracts are signed, for example. It has some OCR. It has some parsing of entities. It can flag risks or inconsistencies across different contracts, so it's kind of full review. And it can, apply different policies on top and so on. And surfacing obligations that those contracts define and so on. So that's one kind of self-contained agent. Now, when you use small models, these task-specific models, you'll find that you use actually a bunch of them to build the agent, right? It's no longer, okay, let's send everything to the same LLM, but you basically identify these task-specific models. They are sort of tools for the agent to solve all these different problems. So in this agent, we have basically a state is in some SQL database, and then contracts come in, we extract things, we store it into the SQL database, and then we do queries against the database when we want to verify different clauses. So there is like a text to SQL model that's doing that. There is an OCR model. There is the Gliner model for entity extraction. There is bigger generative model for some clause risk analysis. And then there is like a planning model over there. There is safety guardrails with the Granite model from IBM and some kind of synthesizer at the end, right? So this agent, I believe, uses 9 models. And that's why it's important for your cluster to be able to handle traffic that's kind of a mix of 9 models. And that's just one agent, right? If a bunch of different teams and people in your organization build a bunch of these agents, now you have traffic that maybe touches 20 or 30 or 40 different models. And that's why, kind of pooling all the compute capacity, loading the models, multiple models on the same GPU, that's the thing that allows you to deal with this super heterogeneous traffic, right? Okay, and this agent, we ran it on some data set with 500 plus real commercial contracts filed with the SEC, and it found some inconsistencies in different contracts, and found was able to flag that it didn't know how to decide if a document is signed or not. So the guardrails kind of work, and so on. This code is available on our repo. So just to finish, basically, when to self-host, I think these are the axes, right? So if you want to process way more data than you are processing today, and you calculated what the bill would be, and the bill is crazy, then self-hosting might make sense. If you are latency sensitive, right? So it's some kind of user-based interaction, and user wants kind of real-time feedback, or the agent is doing so much work that you want to reduce the number of like the time it takes to wait for every single round, you can get big gains by self-hosting and tuning. As we said, the small models are kind of pretty much as smart as GPT 5.1 right now. So if you are not, solving the Riemann hypothesis, but like you are solving some kind of enterprise workflow or support use case or something reasonably contained, then these models are plenty smart. And then, potentially, most importantly, the deployment is yours, right? So you have full control. You will not lose access. If your GPU provider, you don't like them anymore, you just take your thing and put it somewhere else. You are much more robust. You have less platform risk and so on. So I think those are kind of the, if you remember anything from this presentation, then these are kind of the orientation points. So yeah, I think that's it for me. On this QR code or on this URL here, you see the repo of our product. It's Apache 2.0, totally open source cluster for self-hosting of small models, and we would love your feedback and collaboration on that.
Awesome. Thank you, Daniel. Thank you for all that details and information. This is a topic that's close, dear and close to my heart. And I have a lot of questions for you, but I know it's midnight over there, so I won't ask you too many.
We can do.
Yeah, okay. We have about 5 minutes ish. So my first question is, I definitely believe that moving forward, more and more companies will do self-hosting for all the reasons that you listed there, and probably more. What do you see from your research and working with companies? What are you seeing? I'm just curious.
For us, actually, one of the surprises has been that it was the platforms that themselves deploy into different kinds of environments and want consistent inference capability. those are some of the ones who are picking this up the fastest, right? If you are big enterprise and you have been kind of a little bit addicted to the LLM APIs, and it's just quite easy to do another, commit and another buy, and you just kind of keep going. But if you are a company that's either like hitting the hyperscaling inflection and suddenly the bills are crazy, or you are a platform that deploys into environments where you would ideally want to take the inference with you, those were the two cases where people really care.
Gotcha. Yeah, makes sense. Like different companies, they have different level of experience. And then I think I definitely would check out the your Git repo that you share. But I'm sensing that if there is an example that makes it very easy to set up this entire stack, right, as a starting point. And I think that's what you showed earlier. Is that right? Do you guys have a GitHub repo to help with that?
Yeah. So one of the ways you can get into it is you can just take the runtime, the worker, and just start it on your computer. And in our latest release, we made it also natively compatible with the Metal, with Mac Silicon. So if you have a MacBook, you can run the runtime locally. And that's exactly the same runtime with just some dependencies swapped around that then gets deployed into cloud. It's the same models available and so on. So that's an easy way to get in, that you just run it locally. And then the same thing, you run Terraform apply, Helm install, and boom, now you have a cluster that's auto-scaled, all of those different features available in your cloud. So that's one way in. The other easy way to get started is you send me a message, and I'll give you an inference grant for one of our test clusters. So we have test clusters. There is a bunch of capacity. And we are working with independent projects, people sending us cool ideas like, hey, I want to process all this data. I want to build a search system for, German, whatever legislature, stuff like that. We are happy we have this kind of banknotes that we hand out in person. And it's one zettaflop of compute. And we're very happy to sponsor and give people access to those test clusters. So I think those are the two ways.
All right, sounds awesome. I will definitely reach out to you in person, personally. Last question before I let you go. I think I don't know if something like this already existed, but it feels like if there's a course that talks about all these steps that you in this session, you walk through all how to set up stuff like that. Have you considered doing a course like this?
I have joined other people's courses. Actually, one of your presenters today, I think, will join her course. Yeah.